The nature of light has always been an object of human curiosity. One of its greatest secrets was destined to be revealed by the German physicist Joseph von Fraunhofer. Even in classical times, philosophers and scholars made important discoveries about the nature of light. One of them was Ptolemy. In about 135 AD, he noticed that when light passes into an optically denser medium, from air to water for example, it is bent, or as we say today, refracted. Ptolemy's notes made an important contribution to the development of optical instruments. Even so, it was more than 1,000 years before the first spectacles appeared, towards the end of the 13th century. The spectacle makers in the little Dutch town of Middelburg were responsible for the first telescopes, which were developed in the early 17th century. The performance of telescopes was constantly improved as object lenses grew larger, but the larger the lenses, the more obvious their shortcomings. Users were frustrated by fuzzy patches with colored edges. To avoid this problem, makers had to make use of another property of light, namely that most light consists of a mixture of different wavelengths. In 1664 or thereabouts, Isaac Newton shone sunlight through a prism and discovered that the different colors of the spectrum were refracted to different degrees. So, for example, red light with a relatively long wavelength of 700 nanometers is refracted less strongly than blue light, whose wavelength is 390 nanometers. As a result, a lens refracts the short waves of blue light more strongly than the longer waves of red light. This means that the different colors do not focus in the same place. This in turn leads to images of different sizes, one on top of the other, each with its own colored rim. The problem is known as chromatic aberration. In order to eliminate this problem, Newton experimented with various kinds of glass. But he had no success and abandoned his attempt to produce achromatic lenses, in other words, ones that do not display chromatic aberration. The British optician, John Dolland, eventually succeeded in dealing with the most tiresome problems. After experimenting with different kinds of glass, he discovered that certain materials refract light more strongly than others. He combined convex and concave lenses made of different sorts of glass. His achromatic lens refracted all the colors equally. In other words, they all focus on the same plane. The result, a sharp image with no colored rings. Dolland's invention allowed for much better magnification, but there were still no adequate methods of measuring refraction and chromatic aberration. The man who at last provided optics with a scientific foundation was Joseph Fraunhofer. He was born on the 6th of March 1787 in the town of Straubing in southern Germany. Like many children of his social background, he helped out in the workshop run by his father, a master glazier. Of course, that was at the expense of his, in any case, meager schooling. In 1798, his mother died, and just 1 year later, his father. So, by the age of 11, young Joseph was an orphan. The following year, he was apprenticed to the Munich glasscutter Philipp Weichselberger. He was not only a hard taskmaster, but treated Joseph as an errand boy rather than teaching him the skills of his trade. The law at the time stipulated that apprentices attend school on their days off, but Weichselberger refused to allow young Joseph to go. Worse still, he would not even allow the boy to read. Joseph's life was changed by a tragic accident. Weichselberger's house collapsed, burying both his wife and his apprentice. Joseph was buried under the rubble for 4 hours before being rescued. The ruling prince of Bavaria visited the scene in person and made the boy a gift of 18 ducats, a princely sum indeed. Fraunhofer later used some of the money to buy a grinding machine of his own. which he used to practice grinding and polishing glass implements. He owed his theoretical knowledge to a government official named Josef Utzschneider. He had also been present at the scene of the accident and took the boy under his wing. It was doubtless Fraunhofer's thirst for knowledge that moved Utzschneider to insist on the boys being allowed to attend school on his days off. What's more, he provided him with books on mathematics and optics. Utzschneider, together with Georg Reichenbach and Josef Liebherr, ran the Mathematical Technical Institute for the manufacture of precision instruments. In 1806, they persuaded Fraunhofer to join the business as its specialist in optics. The Institute's glass foundry was housed in a former monastery in nearby Benediktbeuern. In 1807, the manufacture of optical glass was relocated there too, with Fraunhofer as the section manager. One of his tasks was to develop achromatic object lenses for telescopes. To this end, he had to measure as exactly as possible the refractive behavior of different kinds of optical glass. In his search for more accurate measuring techniques, he sought to determine the refraction undergone by every single color of the spectrum. This involved him in an investigation of sunlight. In order to obtain as clear a spectrum as possible, he directed the light first through a slit and then onto a prism. Using a converted telescope, he examined the entire spectrum and noticed a large number of thin black lines. There were 574 in total. Later, Fraunhofer investigated other sources of light, but found no lines at all. Eventually, he came to the conclusion that the lines must be an essential characteristic of sunlight. He made very precise notes of his observations. The lines had provided him with very exact reference points for the determination of the refractive indices of different kinds of optical glass. Unlike the colors themselves, they were narrow and clearly delineated. From now on, it was possible to make large achromatic lenses. The Institute became the leading manufacturer of astronomical refracting telescopes, and Fraunhofer himself became well known. He exploited his discovery to investigate the light emitted by planets and stars, because their spectra too had these dark lines. In March 1820, he set up a specially constructed prismatic telescope at the Royal Bavarian Observatory at Bogenhausen near Munich. This instrument was the first to combine a telescope with a prism. The director of the observatory, Johann Georg Soldner, aimed the telescope at a particular star. As soon as the light fell on the prism, Fraunhofer was able to read off its spectrum. It was Soldner too who paved the way for Fraunhofer to become a member of the Bavarian Academy of Sciences at the age of 34. This distinction was followed by others. For example, an honorary doctorate from the University of Erlangen. In 1824, he was personally ennobled by King Max Joseph of Bavaria for his scientific and technical achievements. But just 2 years later, on the 7th of June 1826, Fraunhofer died of tuberculosis. It was the end of a short but highly creative life. In Bogenhausen, Fraunhofer's observations were continued by Jean Lamont, the observatory's second director, using the great refractor on whose construction Fraunhofer had worked before his death. In 1836, using a prism placed in front of the ocular, Lamont succeeded for the first time in analyzing the spectra of less bright stars. In the next few years, scientists began to get to grips with the spectral lines by conducting experiments with colored flames. It was in about 1860 that Gustav Kirchhoff and Robert Bunsen were finally able to decipher the lines in the spectrum. Through the evaporation of minerals, they created colored flames. The spectra of these flames, unlike that of sunlight, did not display all the colors of the rainbow, but just a few regions of it. Each mineral has its characteristic line spectrum. A closer investigation of the solar spectrum revealed that some of the bright lines they had noticed in the mineral spectra coincided with some of the dark lines in the sun spectrum. Among them were more than 60 lines characteristic of iron. They deduced that iron must be present on the sun. But how are these lines formed? The solar radiation, which is generated by nuclear fusion in the sun's interior, penetrates to the surface. In the sun's outer layers, some particles of light are absorbed by the elements present in these regions, swallowed up, so to speak. This causes gaps in the light, missing colors that show up as black lines in the spectrum. Because of the way they are formed, we call them absorption lines. In contrast to these, emission lines are produced when a chemical element, sodium for example, is heated. When this happens, sodium emits energy in the form of light particles of a particular wavelength, which show up as bright lines in the spectrum. Whether produced by absorption or emission, spectral lines reveal the presence of a particular element. Kirchhoff and Bunsen made this insight the basis of spectral analysis or spectroscopy. It allowed them to determine the chemical composition of the sun. Alongside iron, they also detected hydrogen and sodium. The absorption lines were later named after Fraunhofer. His discovery paved the way for the new science of astrophysics. The lines allow astronomers, among other things, to determine the movements of stars and whole galaxies. If a celestial body is moving away from the Earth, its spectral lines are shifted towards the red end of the spectrum. This phenomenon is known as redshift. Bodies moving towards us, by contrast, display a corresponding blue shift. Both phenomena are related to what is known as the Doppler effect. The Austrian physicist Christian Doppler had noticed that a steam locomotive's whistle sounds higher when it's approaching and lower when it's receding. Doppler explained this by the movement of sound waves and their source. If the source is approaching, the waves are squashed, the wavelength becomes shorter and the note is higher. If the train is receding, the waves are stretched and the note is lower. In 1929, this phenomenon enabled the American astronomer Edwin Powell Hubble to show that the universe was expanding. Most of the galaxies he had subjected to spectroscopic analysis displayed a redshift, which would mean they are receding. And the more distant the galaxy, the more pronounced its red shift. One of the greatest challenges facing modern astrophysics is to explain, with the help of spectroscopy, how the oldest currently visible galaxies were formed a good 13.3 billion years ago. All the insights gained by astrophysicists about the origin and future of our universe are gained by analyzing the light of celestial bodies. These milestones of cosmic discovery we owe not least to the tireless curiosity of Joseph von Fraunhofer.